physicist, as Kazina mentioned. I'm not a statistician, and my viewpoint on these things is kind of that of a physicist, but I hope that there's a conversation we can have here. So if you go to almost any talk on this subject, people will show you pretty pictures of networks like this one here. This is the kind of thing we're studying. We're interested in studying this. This is the internet. So it's a network of computers connected together by data connections. Or this is an ecological network. The nodes of species in an ecosystem, the interactions between them. Or this, which is from my own work, this is a social network of collaboration patterns amongst scientists. The nodes represent scientists and the edges represent who's written a paper with whom. What they don't tell you is that this is not what most networks look like. I've specifically chosen some nice pretty pictures here where it's very clear what's going on, because these are rather sparse networks, not too many connections, not too many nodes. You can draw a nice picture of them on the screen of your computer, but if you actually look at most networks, they look more like this. There's some hideous sort of hairball, and you can't really see what's going on at all. They're too dense, too many edges, too many nodes. It's a mess. You can't make a picture of them. Or this is a metabolic network. This is a portion of the World Wide Web. This is a protein interaction network. These are important networks, but they're very difficult to draw a picture of. In fact, I find it a little bit surprising that they even bothered to publish this picture of a network. I'm not sure what you're supposed to learn by looking at this picture here. I don't think you can learn anything, really. It's just too dense. So one of the fundamental questions that we ask in this field is, what do networks look like when you can't actually look at them? It's impossible to make a picture of them. And this is something that statistics is very good at doing. So the basic question is, how can I make statements about the structure of this network? Things that are meaningful to human beings. Take a terabyte of data sitting on my computer, boil it down somehow, and tell you something useful about what the structure of this network is. There's been a lot of work on questions like that. A lot of the work that's been done has focused on small-scale properties of networks, which means things like node degrees. The degree of a node in a network is how many connections it has. That's an easy thing to measure, just how many edges are connected to this node. Or correlations, occurrence of small subgraphs like triangles in the network. Things like this are very simple to measure. I mean, the degree of a node, you just go to the node and you count how many connections. That's all it is. There's no complicated mathematics involved here at all. Even though these are very simple measures, that doesn't mean we should turn our nose up at them. They can also be very useful. You can learn a lot by looking at them. However, that's not what I want to talk about today. What I want to talk about is large-scale structure in networks. Things like, I'll talk about these things like community structure, core-periphery structure, ranking, latent spaces. I'll describe what these things are. But basically, they're ways of talking about the big picture structure of a network. What's the structure of the whole thing? And this is a much more difficult question to answer because obviously it requires you to somehow integrate information from all over the network and somehow combine it together to say something useful about the network. So there are a number of different techniques that one uses to talk about large-scale structure in a network, especially spectral methods, for example, and optimization methods. But what I want to talk about today is inference. So inference in network data means basically what it means in any other kind of data. Typically, it means I'm fitting some kind of model to the data. So I want to infer large-scale structure in a network. I make up a network model, a model of a network that contains large-scale structure, and then I fit it to an observed network. I want to start by talking about what is perhaps the classic example of large-scale structure in a network, what we call community structure. I want to go into this example in a bit of detail so we can get the idea of what's going on here, but it's not the only example I want to talk about. Towards the end of the talk, I'll talk about how we can take the same ideas that have been developed largely in the context of looking at community structure in networks and apply them to all sorts of other kinds of structure as well. But so community structure means structure that looks like this. It's a lot of the networks we look at have nodes that are divided into clumps of some kind. There's a clump here, there's a clump there. There are a lot of connections between nodes within clumps and only a few connections between the clumps. So this might be a group of friends in a social network, another group of friends in a social network, something like that. So a basic question here is, does this kind of structure exist in the network I'm looking at? And if so, can I find it? In other words, can I determine what the clumps are, which nodes belong to which clumps, and so forth? In some networks, that's easy to see. Here's a picture of a social network. It's a friendship network of school kids in a US school. And it's very clear in this network that there are some clumps of nodes. Something going on here, so we can take this network and we can now go and say, okay, let's investigate what those clumps are. There's something interesting going on in this network. But go back to this picture again. Are there communities, modules in this network? Very hard to tell. Like I say, in most cases, the pictures are just too dense and complex to know. So we want some automated way of trawling through large network data sets and picking out this community structure. So this is actually a classic problem in network analysis that goes back to the social networks literature in the 1980s. A standard way of employing inference to solve this problem is to fit this model here. This is called the stochastic block model. So again, the idea is, just like you can learn about data points on a graph by fitting a straight line through them, to learn about the structure of networks by fitting a network model to them. So the idea here is to create a network model which contains the kind of structure we're interested in and then fit it to the data. So the model is the stochastic block model. It's very simple to define. You take some number of nodes equal to the number that appear in the real network that you're interested in, and you divide them into groups, and then you place at random edges between them with probabilities that depend on which groups the nodes belong to. So I might have a probability, I'll call it omega 1,1 here, of edges between nodes, two nodes that are both in group 1. Or omega 1,3, which is the probability of an edge between a node in group 1 and a node in group 3. Now, other than that, the edges are completely independent. So they're independent random variables with probabilities given by a matrix of these omegas. So now the idea is going to be that we fit this to observe network data by varying the parameters in the model. And the parameters are, first of all, these probabilities of the edges, but also there's another hidden set of parameters, namely which node belongs to which group. Right? When I divided the nodes up into groups, I had to say who's in which group. So I'm going to have another set of parameters, discrete parameters. G sub I is the group that node I belongs to. So in this particular case, G sub I would take values 1, 2, or 3, depending on which group node I belongs to. And so I want to now fit this model by varying these parameters in the model. Okay, so I'm going to do that in a moment. Before I do, I want to make what I think is a really important point about the nature of the data we're looking at. All of the networks that we look at, essentially all of the networks that we look at, are so-called sparse networks, meaning that essentially all possible edges that could exist in the network are not there. Only a vanishing fraction of all possible edges is actually present. If you were to randomly choose a pair of nodes, it probably is not connected by an edge. A more mathematical way of saying that is that the number of edges is little o of n squared. Right? If you think of the matrix representation of a network, it has n squared possible elements, and almost all of them are 0. In the limit of large n, it goes up slower than n squared, the number that are non-zero. Another way of saying that, entirely equivalent, is to say that the average degree of a node is little o of n. So the average degree of a node can increase as the size of the network increases, but it does so slower than linearly in the size of the network. So that in the limit of large size, you, a node in the network, are not connected to almost everybody. You're only connected to a vanishing fraction of the rest of the network. This is what we call a sparse network, and all of the networks we look at fall in that category, but that's not the distinction I wanted to make. The distinction I want to make is between that and what I will call very sparse networks. I don't actually know if these have an official name in graph theory, but I'm going to call them very sparse networks. And what I mean by that is networks where the average degree, which I'm calling C here, is order a constant as the network becomes large. In other words, the number of people I'm connected to is not growing at all. And that turns out to be absolutely crucial for this inference problem. If you're in this regime, sparse, where the average degree is growing but slower than n, then it still means that in the limit of large graph size, you have each node has arbitrarily many connections. So I want to infer what group do I belong to. And basically the way you do that is you look at what groups the people you're connected to belong to, and the number of people you're connected to is diverging as the graph becomes large, which means basically every node has a diverging number of measurements, the number of data that help it decide which group it belongs to. So it's not a surprise to learn that in that limit, you can determine the groups that nodes belong to with complete accuracy in the limit of large graph size. In other words, you can come up with a consistent estimator that will tell you exactly what the division of the network into groups is in the limit of large graph size. In the very sparse case, the number of data you have per node is a constant in the limit of large graph size, which means that there's always going to be some error in your estimation of who belongs to which group, which means that just doing simple maximum likelihood is not going to work as the graph becomes large. You're going to have to instead calculate an entire posterior distribution over group assignments. Just calculating the one maximum likelihood one is not enough. So there's an important distinction between what I call sparse and what I call very sparse. In the sparse case, just simple maximum likelihood works well, gives you a consistent estimator. In the very sparse case, you're going to have to do something more sophisticated. You're going to have to calculate a complete posterior distribution. So let's look at that. Here it is for the sparse case. I can write down a likelihood for this stochastic block model, which is the probability of an observed graph given the parameters, which are omega and g. Omega, remember, is the probabilities of the edges, and g is the set of group memberships, who belongs to which group. And then I want to maximize this with respect to omega and g, and traditionally I do that in two steps. The first step is to do it with respect to the omegas, which is easy because they're continuous probabilities, so I can just differentiate. That gives me values for the omegas, which I then substitute back into the likelihood, or if you prefer, the log likelihood, and then gives me this expression here, which is called the profile likelihood, first derived in this paper here. Technically it's the log profile likelihood, I guess. Anyway, the variables here are, so the picture is, you give me a network, and you give me a candidate division of that network into groups, and M sub Rs is the number of edges that run between group R and group S in your candidate division, and N sub R and N sub S are the number of nodes in group R and group S. And there's some just joint sum here over groups R and S. So if I give you a network and I give you a candidate division, you can calculate those numbers, plug it in here, you get a number for this profile likelihood. And then the goal is to maximize that over all possible assignments of nodes to groups. In other words, over all possible divisions of the network into groups. And the one that gives you the largest likelihood is the one that wins. That's a difficult thing to do because that's a discrete optimization and there's an exponentially large number of ways of dividing a network into different groups, so you can't actually do it exhaustively, but there's various heuristic algorithms that work reasonably well. Okay, so the thing you need to know about this procedure is that it's a total failure. It doesn't work at all. For interesting reasons. So here's an example application. This is a famous network from the social networks literature. It's a friendship network. It doesn't really matter what it is, but it's believed to divide clearly into two groups, which is basically the left and right half of the figure as I've drawn it here. If you feed it through that optimization procedure I just described, here's what you get. It divides it into two groups, but they're not the ones you expect at all. Definitely not the left and right halves of the picture. You got totally the wrong answer. Here's another example that I got from my colleague at Michigan, Lada Adamic. This is a web network of hyperlinks between web pages on the subject of politics, US politics, in fact. And again, this is a network which is thought to divide cleanly into two groups, which represents liberal politics and conservative politics. You should be able to derive that by dividing this network into communities, and it totally doesn't work. The accepted division is basically, again, the left and right half of the figures there, and you do this calculation and it just completely fails. So what's gone wrong here is that the model as I described it generates networks where the distribution of node degrees is Poisson, because the edges are Poisson-independent variables. And the distribution of node degrees in the observed network is very far from Poisson. And this is true of most of the networks that we look in the real world. They're often got very broad distributions, not tightly concentrated about the mean. which means basically that there is no set of parameters of this model for which it's a good fit to the observed data. There just aren't any good fits. It's actually not too difficult to fix the model to correct for that. So one can use what we call a degree-corrected block model. And basically what's happened here is where previously I had the probability of the edges, I've replaced it by this combination here. D sub I is the degree of node i's, the observed degree that a node has in the data. D sub j is the observed degree of node j, and the probability of an edge between nodes I and j is now di dj times, again, some probability parameter omega. What this does, you can show, is it creates models. If I'm using this model in the forward direction to generate random networks, it would create networks where the expected degree of node I is equal to the observed degree in the observed network, this parameter d sub I. In other words, roughly speaking, apart from Poisson fluctuations, it matches the generated degree to the observed degree. So it basically takes care of the degree distribution for you, and then this parameter omega is left to take care of the structure of the communities. With that simple change, you can go through a similar derivation to 4 and derive a profile likelihood that looks like this. It's very similar to the one we saw before. The only thing that's changed is down here in the denominator, where before we had n sub r, the size, the number of nodes in group R. I now have this parameter kappa sub r, which is the sum of the degrees of the nodes in group R. In other words, basically the number of edges in the group. So instead of the number of nodes in the group, I now have the number of edges, and it turns out that that's all you need to do in order to fix this problem. Now if I go ahead and maximize this profile likelihood, I get results very close to what I'm expecting. Division of the network roughly down the middle, same for that network of blocks. Okay, so this works nicely for the sparse case. But it's not going to work for the very sparse case for exactly the reasons we described, that the distribution over assignments of nodes to groups is not sharply peaked in the sparse case. There's always going to be some error in your inference, even in the limit of large graph size. In order to do that, we need to look at an entire posterior distribution over group assignments. So we're still okay as far as the probability parameters omega in the model are concerned. There's only a fixed number of those, and so in the limit of large graph size, we can still find a tightly peaked estimate of those, which is consistent in the limit of large graph size, but the group assignments themselves are the problem. We're not going to have a tightly peaked distribution of those. So instead, we need to calculate a complete posterior over the group assignments, which means that we need a sort of lopsided approach, which combines a sort of ordinary maximum likelihood estimate of the probability parameters with an estimate of the posterior distribution over the group assignments. So we're doing this sort of asymmetric thing, and an ideal approach for doing exactly those kind of things is an EM algorithm, which does exactly that. It treats two sets of parameters, one using ordinary maximum likelihood and one using a posterior distribution. So you can write down an EM algorithm for this problem. Being a physicist, I tend to think of it in physicsy terms. It's equivalent to the maximization of what physicists would call a free energy. It has an energy term and an entropy term, and the two compete against each other. So in this expression here, everything is the same as before, degrees and probability parameters and so forth. There's a new quantity here I'm denoting Q of G, and that's our posterior distribution over group assignments. And you're doing a double optimization of this thing with respect to both the parameters and this distribution. So now you're not optimizing over the group assignments G themselves as you were before. You're optimizing over the probability distribution over the group assignments. And that joint optimization can be done, show that it's just equivalent to these two equations here. The one on the left gives you the probabilities in terms of the posterior, the one on the right gives you the posterior in terms of the probabilities, and you just alternate between these two until you get convergence, and that's your standard EM algorithm. The catch which is true of almost all applications of the EM algorithm, is that this equation here that gives you a posterior distribution, it has an intractable sum in its denominator there. This sum in the denominator is the sum over all possible ways of assigning nodes to groups, and there's an exponentially large number of those. So we can't do that numerically, for example. It's just too big. So the traditional way to deal with that would be to use Markov chain Monte Carlo. And you can do that here too. It works fine. But I want to discuss an alternative method that was proposed recently by these people up here. So this is not my work now, but it's a very nice piece of work, so I want to talk about it anyway, which uses message passing. So in the interests of time, I won't go through the derivation here in detail, but let me give you sort of the overall idea of what this method does. Basically, so we're interested in calculating this posterior distribution over group assignments, right? What's the probability that each node belongs to each group? The way message passing works is that every node in the network maintains a set of probabilities that says that's the probability, the posterior probability that this node belongs to each possible group. And then the algorithm works by each node looks around at its neighbors in the network and it says, what groups do you all belong to, all you neighbors of mine? And then based on what groups they all belong to, I estimate the probabilities that I belong to each of the groups. And everybody else is doing this at the same time, so everybody updates. Based on looking at their neighbors, they make an improved estimate of their probabilities of belonging to groups. And then you just do it again, and you just keep on doing it until the thing converges to something, and you end up with a self-consistent set of probabilities where everybody's sort of satisfied with their estimate based on what their neighbors are saying. So the derivation is not very hard. It's just sort of repeated applications of Bayes' rule. You end up with these equations here. It actually doesn't really matter very much what the structure of the equations is, but basically the probabilities are expressed in terms of the probabilities of your neighbors. So this method works nicely. It's significantly faster than applying Markov chain Monte Carlo in this case. I mean, this network is This method is specific to networks. This is something you can only do on networks. You couldn't do it in general applications of the EM algorithm, like to mixture models or something like that. But for networks, this works very nicely, especially for sparse networks. In fact, its particular strength is it works on sparse networks because the sparser the network, the fewer neighbors you have that you have to poll in order to calculate your probabilities. So the amount of work actually just goes up linearly with the amount of edges in the network. So you have a small number of edges in the network. You can do this very quickly. Here's just one example application of this from a recent study I did with a sociologist named Elizabeth Brooke at the University of Michigan. And here we were studying a network of messages exchanged between users of an online dating website. So there's a large US website where, people can post pictures of themselves and a short description, saying I like long walks on the beach or whatever, like that. And then people can exchange messages. You look at other users of the website, and if somebody looks good to you, you can send a message saying hi. So we have a large data set of messages on the site, and it's big. So there's sort of 10 million users of the site, of whom 4 million were active at the time we gathered the data, and there are about, tens of millions of messages exchanged between them. So we're talking about a large network here, and yet it's still possible to do these calculations quite easily. They take a few minutes on a standard desktop computer. What I'm showing here is an example application where we did one of these community structure calculations for networks of messages exchanged in various US cities, and we divided the network into 8 groups in each case. And what we found was very consistent across cities. In each case, we found that it divided into 4 groups of men and 4 groups of women. And the groups are clearly corresponding to age divisions in the network. In each case, we found there was a group of lower 20s, a group of upper 20s, a group of 30s, and a group of 40s and above people on the site. And that was very consistent across the different cities we looked at, suggesting that this is a fairly robust kind of structure. So in other words, it's telling you, remember the definition of a group is that most of the connections are within the group and few of them between the group. So it's basically telling you that people tend to express interest in other people who are about the same age as them. And once you know that, then you can ask all sorts of other questions about the statistical composition of these groups. For instance, I can ask questions about the messaging pattern, which groups are messaging which other groups, and how much, and do they get a reply, and all sorts of things. There's all sorts of interesting questions you can ask about these data once you get into it. Okay, so this works nicely as a practical method for rapidly analyzing large networks. But it's not only that. One of the nice things about this message passing method is that it also serves as a starting point for further analytic calculations about network structure. So I just want to tell you about this very nice piece of work done by Aurélien Dessel and his collaborators at Paris, where they took this belief propagation method as a starting point, and they made the following argument. So again, it doesn't really matter what the structure of the equations is. Remember, the basic idea is just that each node looks at its neighbors, asks them what groups they belong to, and on that basis, they decide what groups they belong to, and then you just keep on iterating this thing until it converges. Just knowing that, it's clear that one possible way that this thing could converge, one possible fixed point of that iterative process, is that everybody could just say they belong to all groups with equal probability. Say, for instance, I have just two groups. Everybody in the network says, I belong to each of these two groups with 50-50 probability. Right? So if I look around all my neighbors and they all say, oh, I'm 50-50 in group 1 and group 2, then what am I going to conclude? The only thing I can conclude is that I'm also 50-50 in group 1 and group 2. There's nothing to tell group 1 and group 2 apart at all if everybody says they're 50-50 in either group. So that means I also conclude that I'm 50-50, and so does everybody else in the world. So on the next iteration of the algorithm, we're all still saying 50-50. This is a fixed point of this. So if that happens, then the algorithm has failed, right? Because everybody just said, I'm 50% in group 1 and group 2. You learned nothing about who's in which group. So that is a fixed point. That is a possible thing the algorithm can converge to. And if it does converge to that, it has failed to tell you anything at all. So it becomes crucial to know whether that fixed point is an attracting fixed point of the iteration or a repelling fixed point. If it repels, okay, you're fine. You're going to go to some other fixed point. But if it attracts, your algorithm fails. So the calculation they did was actually extremely simple. They just took this idea and they did a linear stability analysis around that fixed point, which turns out to be easy to do because it's a very symmetric fixed point. You can just do the derivatives, calculate a Lyapunov exponent, and they showed that if this condition is satisfied, well, it doesn't really matter what the variables are. It says if the structure in the network is sufficiently weak, this condition is satisfied, the fixed point will become stable and your algorithm will fail. What that's saying is that if there's strong structure in the network, you can detect it by this means. If it's too weak, but non-zero, still there, but weaker than a certain point, then your algorithm fails. So that in itself is a nice result, but it's actually much more powerful than that, because what they then did was they took this algorithm and they applied it to networks that were themselves generated using the stochastic block model. So you're generating, so it's a consistency result. You're generating data using the model, and then you're fitting it using the same model. Well, the best way to get the parameters of any model is to fit the data to the model that it was actually generated from. There's no better way of doing it than that. So, in other words, to detect the structure that they were planting in the network by generating it using the stochastic block model, there's no better way than employing this algorithm. And that means that if this algorithm fails, all other algorithms must fail as well. Net result is there is a regime of networks where there's structure in the network. You know it's there because you planted it there, but it's impossible to detect it by any means. Any algorithm will fail in this regime. So this is a new and interesting class result. It's an existence proof that there can exist structure in networks which is undetectable by any means. You know it's there, but provably no algorithm will detect it. Here's just a quick example of that happening. This is from my own work. This is a completely different algorithm. This is done using a spectral method, so a completely different class of techniques, but it also detects community structure. And basically what you're seeing here, this horizontal axis measures strength of the structure, and you're seeing the algorithm fail at various different points for different parameters of the model. But you can see these very clear phase transitions where the algorithm fails, and those phase transitions occur at exactly the point predicted by this message passing calculation. So this is a completely different class of algorithm using a completely different set of methods, but their claim was, well, our results apply to any algorithm, and it certainly seems that that's the case. Here's a completely different kind of algorithm, still fails at exactly the predicted point. Below that, we are completely unable to detect the structure in the network, even though we know it's there. So I believe that Marc Lalage is going to talk more about related things to this later on. But in the last few minutes, I just wanted to talk about some applications of similar kinds of ideas to other types of structure in networks. I've been talking about community structures so far, but let me talk about some of the other things that you can do using inference methods. So first of all, a very slight variation on what I've been talking about is applications to uncertain data. So far we've been assuming that you know the observed network exactly, but of course in science you never do. There are errors in your measurements. So we have to assume that your data may be uncertain. In network terms, what that means is when I say that there's an edge between two nodes, maybe there isn't an edge there. Maybe I'm only 90% certain that there's an edge there and 10% probability that there could be no edge there, even though I think there is. Right? So uncertain data in this context would be represented, instead of just having zeros and ones for lack of connection or connection between two nodes, you'd have some probabilities which could take values anywhere from 0 to 1. So we'll represent those probabilities by Q sub ij. Qij is my estimate of the probability that there exists an edge between nodes I and j. So I can handle these in a similar sort of way. I can write down the probability of the data, that's the set of probabilities, given the parameters of the model, and that can be written in terms of the probability, the original probability of a graph given the parameters of the model, the same thing that I also wrote down earlier, the standard likelihood, times the probability of the observed data given the graph. So the graph itself, capital G, is unobserved here. I'm just going to sum over that to get the probability of the data. So this probability here of the data given the graph, you can think of as being some sort of noise function. It takes the real graph and it messes it up somehow so that my measurements become uncertain. The catch is that we normally don't know what this noise function is. We don't know what the mess in our experiment was that caused our data to become uncertain. The nice thing is it turns out that that doesn't matter. When you do this, it turns out essentially that this calculation, this function here cancels out except for some overall constants which don't matter. And so it's possible to write down an EM algorithm and do inference on this model as well. And it turns out that once you do that, you can substantially improve the quality of your inference over inference based on just assuming that the data you saw are actually correct, the naive assumption that there's no error in your data. So this figure here, for instance, is just showing a comparison of sort of the fraction of nodes that you assign to the right groups in a sort of cross-validation type test where we knew what the answer was supposed to be. This over here is an ROC curve showing it improves a bit when you allow for uncertainty in your data. So that's really just a very small change. Here's a slightly bigger variant on the problem. Sometimes when I'm looking for community structure in networks, I don't just have everybody belongs to separate groups. Sometimes I have overlapping groups. So I've been assuming that the groups are disjoint. Everybody belongs to exactly one group. But it's certainly possible, for instance, in social networks, that you could belong to more than one group. You could belong to the group of your college friends and the group of your co-workers and the group of your family and so forth. So we can generalize our models to that case as well, which I do by, the way we do it is actually by generalizing the degree parameters that measure how many connections a node has. Now we generalize them to say that each node has a number of connections of different kinds. You have your family connections, you have your co-worker connections, you have your college friend connections, whatever. So we have a set of degree parameters now which say the number of connections that node has of type R. And then I can write down a log likelihood there, and I can write down an EM algorithm for this as well. And then I can do divisions of networks like this one here, which said I divided this network into two groups, and almost everybody in the network belongs to one group or the other group, but there are some people sort of down the border here who are not quite sure what group they belong to, and I can sort of get a percentage by which they belong to each of the two groups. Here's a slightly more complicated example. Some of these people belong to several different groups in different percentages, like this person here belongs to 4 different groups, potentially. Okay, that's still doing community structure. There are other kinds of structure altogether. Fairly simple one is core-periphery structure, which is where I have dense, well-connected nodes in the middle of the network and sparser, less well-connected nodes around the outside. This is something that sociologists often talk about. This one, in fact, can be inferred using basically the same approach. You can infer it using the stochastic block model. The structure of the probability parameters is different. They're sort of dense in the core, medium from the core to the periphery, and very sparse in the periphery. But it's basically the same model, just with a different choice of parameterization. So we can infer it using the same kinds of methods. Taking things a little bit further, hierarchy occurs when I have a network that divides into some set of groups, but then the groups divide into smaller groups, and those groups divide into smaller groups, and so on. Turtles all the way down. This can be represented using a tree-like structure, like this binary tree on the right here, where the node at the top represents the whole network, and it splits into 2 pieces, and those pieces split into pieces, and so forth. You get all the way down until at the bottom level, you just have individual nodes. So this can represent structure in the network on all scales, from the scale of the whole network all the way down to individual nodes. It's kind of analogous, however, to community structure. You still have probabilities for the edges, and then the role of who belongs to what group is now played by this tree structure. So you want to do sample the posterior distribution over possible trees, which you can do, for instance, using Markov chain Monte Carlo again. There are standard Monte Carlo methods for sampling trees. So you can do that. You can feed in a network, and you can determine what the best fit tree is for that network. I actually don't find pictures like this terribly helpful, so you can draw them in other ways, like this, same network. But now the boxes represent the groups, and then boxes are divided into sub-boxes and so forth. So I can determine groups within groups. Here's another example. This is something that we've been working on just recently. Latent-space structure is where the nodes in a network are hypothesized to lie somewhere in some space. For instance, it could be a Euclidean space, but it doesn't have to be. And then the probability of connection between nodes depends on where they are in the space. So it's kind of like community structure, where the probability of edges depends on which groups you belong to, but it's now a continuous space. So we can infer this as well by writing a model which is in some ways analogous to the block model. You give each node a position in the space, and then the probability for connection between 2 nodes depends on their positions x and y in that space. This omega now is some continuous function instead of a discrete matrix of probabilities. So we represent it by doing a basis expansion in an appropriate set of basis polynomials. And then the EM algorithm acts on the coefficients of this expansion. The EM algorithm is a bit more complicated now than it is for the simple stochastic block model, but it's straightforward to write the program. You can do it, and it works quite nicely. Here's just one example. I fed it the network of motorways in the United States, and the colors represent the inferred positions of the nodes in the latent space, and clearly what it's discovered here is some sort of axis that runs from east to west across the country. In other words, it's worked out that there is a geographic basis to this network, and it's inferred one of the coordinates of the geography we only told it the topology of the network here, and it's inferred the geography by looking at the topology. Here's another example. This is a neural network of neurons in a worm, the worm C. elegans, the only organism I know of whose complete neural network has been mapped. And the colors, again, represent inferred positions, and as you can see, they correspond quite well to the actual positions of neurons in the body of the worm, but again, inferred only from the topology of the network. I'm just about out of time, so let me give you one more kind of fun example. This is an application I did with my student Brian Ball to a network of friendships amongst kids in a US high school. And one of the things about when you study friendship networks is the data are a directed network. You kind of think of friendship as being an undirected thing. You know, it's a two-way street. If two people are friends, it goes both ways. But when you study it empirically, what you typically do is you just go ask people who you're friends with. So the fundamental unit of data is A says that they're friends with B. Right? So it's a directed relationship. So what you find is quite often B doesn't say they're friends with A. So you get these sort of one-way friendships, and traditionally in sociology that's been looked at as a data defect. There's just something wrong with your data. Either A and B are friends or they're not. If it only goes one way, then that's because something is missing from your data or people are misreporting or something. Our hypothesis was that no, actually there's some information there in the directions. The directions are telling you something. So we formulated a directed version of this latent space, Inference, and what we discover is that in every case, we looked at 84 different schools. In every case, there's very strong latent space structure there, such that there is a ranking of the kids in the school from low to high, such that all these one-way friendships go from a lower-ranked person to a higher-ranked person. On average, averaged over the 84 schools, 98% of the directed edges went from lower rank to higher rank. 2% of them went the other way, so it's a really strong effect. So the hypothesis is that what we're seeing here is sort of some level, sort of pecking order, social hierarchy, that people lower down the social hierarchy want to say they're friends with people who are cooler than them, but the cooler people don't want to say they're friends back. And there's some evidence that that's the case. Here is just empirically measured distributions of sort of the difference in ranks between people who say they're friends. And what we find is, left plot is for people where the connection went both ways. Both of them said they're friends. In that case, we find in almost all cases that their inferred ranks are very close together. If two people both say they're friends, then they're at exactly the same level in the pecking order. That's why this spike is at 0. The delta is at 0. If only one of them says they're friends, then you again find a spike at 0, but you also find this long tail off to the right, which sort of dies away. It's people saying they're friends with people who are a bit higher up the pecking order than they are, but not much higher. Right? It falls off. It's like you don't say that you're friends with the coolest kid in the class, because nobody's going to believe you. You say you're friends with somebody who's just a bit cooler than you are. So the hypothesis is that this inferred ranking corresponds to some kind of social status, and there's evidence that that's true. For instance, it correlates strongly with in-degree in the network. In other words, the total number of people who said they're friends with you, just total popularity. More popular kids are higher up the ranking than less popular kids. It also correlates strongly with age. So age in American school is measured in grades, 7 to 12, in this case, which is like ages 12 to 18 or something like that. And it's well known among sociologists that older kids in high schools have higher social status than younger kids. So that's absolutely a thing, and indeed our inferred ranks correlate strongly with age. Here's just one example of what the networks look like. So the youngest kids are at the bottom, the oldest kids are at the top, and most of the edges point upwards in the network. I'm out of time. I have to stop talking now. Before I do, let me just say thanks to my terrific collaborators, a bunch of students in my group, 2 postdocs and 2 faculty collaborators. Thanks to you for your attention. That's it. I'm done.